Suppose there is a wall. So wall here. This is the ground. So there is a wall, and let's say a boy stands in front of the wall, and he pushes very hard at the wall. Okay, so he pushes very hard with as much force as he can. Let's say with show his own weight on it and even more. So let's say he's pushing it with a force of say 1,000 newtons, maybe. Okay, huge force is applying there, but the wall doesn't move. It's a brick wall, tough. The wall doesn't move at all. Question: if he keeps pushing very hard for 1 hour, how much work has he done? Now, obviously, we would think that he has done a lot of work. He's going to be really tired and really tired after the 1 hour. He must have done a lot of work. Now, that's what we would think in everyday, in the way we use this word, this work, use the meaning of work in everyday English. But in physics, work is defined specifically as the force times the distance moved. Defined as force times distance moved. Now, in this case, the boy might be pushing really hard with a big force. This big force of 1,000 newtons. Okay, assuming that he is that strong. But because the wall has not moved at all, the distance is 0. The distance is 0. So therefore, the work done is 0 joules. Now that must be really difficult to understand. The boy has clearly used a lot of energy. He's been standing there for an hour and pushing really hard. How can we say that no work is done? Right. Now, to understand this, we need to be quite precise about what the work here refers to. Now, the work here, as I use it, refers to the work done on the wall. The work done on the wall. Now, the boy might be all tired out and aching after the 1 hour, but he might have been doing lots of work on his own muscles and maybe even his own bones, which might start creaking after that. But as far as the wall is concerned, as far as this wall is concerned, the wall hadn't moved. No energy has been given to the wall at all because of this work done, because of the force from the boy. So as far as the wall is concerned, no work has been done. It hasn't moved. It hasn't gained any energy. It hasn't done anything like that. So this is the work done on the wall, and it's 0 joules, and that is correct. The wall hadn't received any work and hadn't gained any energy. So the work has been done. The boy has done on his own body, and he's really tired out because of all the work that his muscles has been exerting, and so on and so on. So this is the one thing we need to really be aware of when we use this term work in physics. Now, with this understanding, let's extend this idea a little bit. Let's extend this idea a little bit. Let's say this time this boy is pushing at the box. So alright, so boy standing here, okay, and he's pushing at this box, and the box moves. Let's see, pushes at the box moves. Okay, this time the box moves. Now let's say this boy is pushing, he's applying a force in this direction. Let's see, he's applying a force in this direction, because as you can see, he's a lot taller than the box, so when he pushes, he has to bend downwards and push at the box, at this corner of the box. So naturally his force would be in a sort of a slanted direction, right? In the direction, partly in the direction that he's moving, but also directed at an angle, and not really directly towards the horizontal. So, and the box, right? The box then moves. The box moves and comes here after some distance. Okay, so the box comes here after some distance. Let's say the distance moved by the box. Let's say this distance is 3 meters. 3 meters. Okay. So this time the box is moved. Now, suppose that this force is pushing it with a force of 50 newtons. Force of 50 newtons. Now let's think. If I want to find the work done by the boy using this same formula, I would take 50 times 3, 50 newtons times 3 meters, and I would expect to get 150 joules. That seems obvious looking at the formula, but let's think about this a little bit more. Let's think about this a little bit more. Now, if I have this force, which is at this angle, we can think of a force. We can think of resolving a force into its components. So let's say I want to resolve this force into a vertical and a horizontal components. So what I do is I think of a horizontal line and a vertical line. Okay, vertical line. I draw a perpendicular from this force, this arrow, to each direction. Then this vector here will represent the horizontal component, and that vector here would represent the vertical component. Okay, so I can think of this 50 Newton force as a resultant of those two components. Okay, so these two components together has the same effects as the 50 Newton force. Now let's say this horizontal component is 40 newtons and the vertical component is 30 newtons. Now let's think about the effect of each of these forces separately. Let's think of the 30 Newton force first. Now this 30 Newton force is the force that is pushing downwards. that is pushing the box downwards. 40 Newton force pushes it horizontally. So clearly, if I have a 30 Newton force pushing the box downwards, the box is not going anywhere, alright, because there is the ground here. The box can't go through the ground, okay, unless it's a thin piece of wood and the wood breaks. Right? On a normal ground, the box would not move at all if we push down 30 newtons. Now, as we have learned from this wall that did not move, no matter how hard the boy pushes on the wall, if the wall does not move, no work has been done on the wall. So this 30 Newton force that pushes the box downwards, because the box hadn't moved downwards, so the 30 Newton force does not do any work on the ball at all, or on the box at all. Okay, so this 30 Newton force is basically not really doing any work. Okay, but if you look at the 40 Newton force, this horizontal force moves the box. Right, it is this 40 Newton force that moves the box over the 3 meters, and that means that it is the 40 Newton force that's actually doing the work. So to be correct, we should not have taken the 50 Newton, this slanted force. We should have taken the component of the force in the direction of the movement when we want to calculate the work done. So instead of 50 newtons, I should have taken 40 newtons. So I get 40 times 3, and that's 120 joules, and that would be the correct answer in this case. So with this exercise, we learned something new about calculating and the meaning of work done. We learned that we can't just blindly take the force on an object and multiply by the distance it moved. We have to think about the direction. Okay. Now, in this example, as I have described it, what it tells us is that we should that the force we use to calculate the work done should be the component of the force in the direction of the motion or of the displacement of this displacement of 3 meters to the right. So this is one way I can describe this observation or mean this more precise meaning of the force of work done. I can say that work is equal to say the component of force in the direction of displacements okay, that's quite a long description. Component of force in the direction of displacement times the displacement, the displacement.